Thanks, Derek. So, wouldn't be Survey without me talking about SPA. So here we are. I'm going to talk a little bit about some work that Dan Moriarty has done at Brown as part of his PhD work, and now that he's transitioned to being a postdoctoral student, researcher, and integrating some of that work into some of the sort of larger questions that really started raising back at LPSC. So for those of you that remember my LPSC presentation, that's a little bit better than I can do because I certainly can't remember at this point. And I might have to just give it again if we don't have any slides up. But what I'd like to do is sort of follow on with some of the questions that are raised regarding the origin of some potentially older surfaces within a central portion of SPA. And ultimately, what I'd like to do is show my first slide. But the larger question really is trying to unravel the magmatic history of not just the moon, but specifically of SPA. And Jim raised a lot of good points about distribution of floor fractured craters and really unraveling some of the secondary processes that have shaped the interior of the basin. As many of you may recall, much of my thesis work and early work was on sort of the role of impact ejecta emplacement and mixing to form a regolith layer and a megaregolith layer. So the work that I've sort of followed up with that is trying to investigate whether or not we see any evidence for massive ejecta deposits within the center of SPA. And I can give the punch line. There we go. Oh, thank God. Okay. So we're going to be looking at the central portion of SPA right in here. This is the beautiful Lola topography that gives us a sense of the shape of what's to come. So next slide, please. Next slide, please. It's a great slide. We'll just leave it up for a little while. It's okay. But the ultimate story here is we want to try to unravel what Dan presented at LPSC. And if you remember the session at LPSC, Dan was talking about the South Pole-Aitken composition anomaly, SPACA. And he hypothesized that the SPACA, which is a calcium-rich pyroxene within the center of the basin, slightly offset from the main topographic depression in the center of the basin. The Apollo Basin is up in here. The center of SPA is roughly around here. He hypothesized that the SPACA, this compositional anomaly, is a magmatic construct that overlies the magnesium pyroxene-bearing floor material, so that we essentially have a secondary crust, a magmatic layer overlying the SPA impact melt. He used central peaks sticking out of several craters, bows, and babas, particularly to constrain the thickness of the SPACA unit to being several kilometers thick. This followed on much work that he did in a paper last year talking about the mafic mound feature, formerly known as Olivine Hill. And what he did some really clever work looking at the band centers, the 2 micron and 1 micron band center at a number of craters across the center of SPA, and showed that the mafic mound feature, which is a topographic positive feature, was not is not related to an impact cratering process, but is indeed this volcanic construct. He looked at several craters across SPA and basically categorized them into three different varieties: flat-floored craters, filled craters, and then a hummocky floor crater. And looking at compositions of the floor material as well as the wall material, showed that that there's very constant differences in the flat-floored craters and the buried craters between the floors of the composition of the floor of the crater is very similar to what he sees across the mafic mound material, and that the walls of those craters are somewhat distinct. And so that his hypothesis was that the fill material that filled these types of craters is related to the mafic mound or compositionally similar to mafic mound, but actually is distinct from some of the surrounding material. So that there's sort of a two-step process. But that in the hummocky floored craters, there's actually no trend, that the compositions are somewhat distinct and separate from what he saw at mafic mound. So this is again really interesting work to pull apart an evolution of composition over time within the central SPA. Okay, so Jim gave excellent sort of overviews about 4 fractured craters, which if I say it fast enough will not come out correct ever again. And there's also recent work by Tron et al. Looking at concentric craters across the surface of the moon. And I really want to sort of focus on both of these sets for a moment, because in looking at some of these craters, and Tron mapped out these bulbous craters, which have a very rugged, rough interior. And again, the hypothesis that they put forward is that these are all modified by volcanic infill. Now, I, being sometimes a bit of a contrarian, like, so how much can we ascribe any of the resurfacing to ejecta infill? And we're all familiar with some of the work looking at radial ejecta decay around, for instance, the Oriental Basin, where we see filled craters, and using the amount of fill to estimate the thickness of ejecta deposits. Of course, always going back to the original geologic mapping, and the original map of this area by Don Wilhelms et al. In 1979 showed that some of these filled craters, and particularly this IFC unit, was hypothesized to be caused by either impact melt deposits that shrank to cause the fill, or that there was this tectonic uplift. So I wanted to investigate whether or not I could sort of pull apart how much fill in some of these craters would be caused by either ejecta emplacement or by volcanic infill. So this is an area in central SPA. We've got the Baba crater here in Stony, and just even looking at the morphology of these features, you can potentially pull out that there's differences. We have these beautiful, flat, filled craters that sort of are just, at first glance, say, okay, yeah, those are filled by mare infill. I can sort of get behind that pretty easily. But then we have these secondary craters, these bulbous craters that are sort of scattered around the center part of, well, all over, but especially right in here. And so, well, can I ascribe any cause of their infill to be from crater ejecta? And so I was going in the hypothesis, I would say, okay, I'm going to be able to see that this is true. So using some of the crater scaling laws derived and shown in Pike 77, can estimate basically what the crater depth should be versus what it is today using the high-resolution topography data that we have, and basically estimate a rough guess or make an estimate of how much fill must have occurred. So we have this wonderful example of a crater that's essentially pristine. It has zero fill. It's a wonderful crater, and then a lot of its doppelgangers around the interior. And it turns out that most of these craters have in the range of 1.5 to 2 kilometers of fill. So I thought, okay, 1.5, 2 kilometers of fill. Let's see how much ejecta we can get there using some of the ejecta scaling laws that have been worked on over the past several decades. And basically, if you were to say, okay, let's take all of the basins on the moon that we know to exist, and how much ejecta do they in place here? Let's take 200 craters around the interior of SPA larger than 10 kilometers in diameter, and estimate how much material comes to, say, this point here. Well, we have, for this one example here, we have about 1.5 kilometers of fill. Well, only about 40 meters of material we expect to come from basins here, 50 meters from SPA craters, and while Stony and Baba might be large in the sense that they're 50-kilometer diameter or thereabouts, you're not getting a lot of ejecta from those craters. So ultimately, the hypothesis fails. Ejecta can't explain all of it, maybe some of it, but not all. So really that leads me to believe that, okay, at some point we have to conclude that there's been some magmatic process to fill much of these craters. And that does tie in nicely with the idea that to the south here we have the Mafic Mound, and certainly that this was a volcanically very active area. So let's take a broader view for a moment and look at the sort of the region and what we can tease out about what's been going on here. So this is the 3-color composite, basically to highlight some of the albedo differences going on in the area. I've outlined the compositional anomaly that Dan presented, and again we're focusing on the region in here. Now it should be, at first you notice that there certainly are very dark deposits. That this is Apollo Basin. You can see the mare portions of the basin filled by mare, and some other mare deposits in the central region here. We've got crater rays that are transecting the region. What can some of these other data sets that we have now tell us about what's going on? So let's zoom back in to the center of the basin, back to the morphology, and again we see that there are these nearby fairly clear, what I would consider to be sort of typical, very familiar mare basalts. Mafic Mound is to the south here, and it is, as Dan pointed out, this topographic high. This is a very highly stretched Lola, actually it's the joint Selene Lola DEM, which really provides some just incredible context for what's going on here. And ultimately, it appears in both the morphology and the topography that we have the topographic high affiliated with Mafeck Mound, which sort of grades down into a smoother region to the north, which has been mapped by Jenny Whitten as being cryptomare, as well as some very clear mare deposits in the region there. And of course, here's our beautiful set of filled craters. Now let's look at some other derived data products now. This is a titanium map using the WAC color filters. Sato et al. In 2015 described the process by which deriving this algorithm in an LPSC abstract. And some things come out very clearly. So again, we've got what sort of we call our familiar mare-filled craters, and then sort of a regional, not high, but an intermediate low titanium surface around Stony, and to the north of that, where we had that smooth deposit. You'll notice that Mafeck Mound is, like typical highlands, very, very low in titanium, but we do see variations that in some regards correlate to what we see with the sort of the topographic smoothness of the region. So this is interesting. So we definitely have evidence for some secondary processes. I should note that there's a little high spot in here, and that's an isolated, very small pond of clearly, I would say clearly of some volcanic material here. So this is pulling out that there are very significant differences going on in this small region that maybe aren't necessarily apparent when you look at just the albedo or morphologic features. This is a map of diviner-derived rock abundance that Josh Banfield's produced. And another I think it's interesting anyway, a very interesting trend is I think apparent that you see in areas, so you see lots of small blocky craters, and that means that there are rocks at the surface 50 centimeters in diameter or larger, and at the abundance of about 3% around numerous small craters. You'll notice on the floors of larger craters where we expect there to be relatively young, billion-year-old or older impact melt deposits, as well as to the north here where we have those extensive mare and cryptomare deposits. We see lots of small little craters. That is comfortable. We have thin regolith in these areas, and so we expect there to be blocky craters. But over a much larger area around Mafeck Mound, we see that there are no small blocky craters, suggesting an older, thicker regolith. So I would suggest that we have sort of a nice way to pull out where cryptomare is, where there's at least older, potentially volcanic deposits related to Mafeck Mound. And so in summary, you know, I think I've sort of at least convinced myself that we don't have a lot of evidence for ejecta causing much of the crater fill, that it's related to volcanics or tectonics. If Spaca is entirely volcanic, we, I think, show that there are extensive eruptive phases with changing compositions and changes in albedo that Dan described in his Mafeck Mound paper. We have an older terrain related to Mafeck Mound, lower in titanium abundance, higher reflectance. We get to subsequent darker, higher titanium abundances, and changing in pyroxene compositions over time. What we need to do next is really show through some detailed crater counts that there's significant age variations of the units, and then try to work in what is causing some of these compositional variations. Is it related to mixing of cryptomare and other deposits? And that's my time for today. Thank you. What's that?
One question?
Oh, David, the check is in the mail. So that's a great, actually, it's a really important question because I'm not a mapper. The mapping community is very tight, and I'm trying to weasel my way into the community. Scott Mest has been funded through LASER to produce a geologic map of the South Pole Quad. Eileen Yinks is producing a geologic map of the western quadrant of SPA, and as of last week, I happen to know that a proposal has been submitted to a NASA program to fund the production of a geologic map of the eastern quad. So it's underway. Scott's Mest is in review, Eileen's map is near completion, and that eastern quad has not been started yet. Excellent question.
What should be done?